the free electron problem, doping of semiconductor, transport and electrical properties, the junction semiconductor, which is the PN diode, and will as well do the junction of semiconductor with metal, and the field effect transistor, which is similar to the bipolar junction transistor as a transistor, but it's different depending on the field, electric field. And it is two types that we will look at, the junction field effect transistor and the metal oxide semiconductor field effect transistor. All these topics are taken from the semiconductor devices, physics and design by Mishra and Sin, so you always can refer back to your textbook. Your textbook is already in the class material. I have downloaded for you. So the first 5 chapters of the text is from 1 to 5. Then this point 6 is chapter 8 and 9 in your textbook. Because in between there is the bipolar junction transistor, which we will not cover in this course. Okay, before we start the lecture then, we will introduce semiconductor. What do we mean by semiconductor? As you know, a conductor, when we say a conductor material, meaning that it has low resistivity, so the flow of current will be much high, while insulator have a high resistivity. That means it's a blocker, meaning the will have low current. So the semiconductor then, it's an intermediate resistivity, so it's between conductor and insulator, and it have a crystalline structure. Of course, most of you have heard about semiconductor when we did the application for the devices. In here we will talk about more physics, so the whole figure of this course is to understand and to learn how the electrons really behaves inside a semiconductor, what's the relationship between electrons and the current flow, and the junction, the depletion region even in semiconductor. So at first what we will do is we'll study the electrons in free space, then we will implement the electrons inside semiconductor, and from there we can learn how we can physically understand all the behavior of electrons. Okay, so the first lecture then today will talk in general about material properties, the crystal structure, although I'm not going to go in detail in the crystallographic notation or the crystal structure, since in solid state physics we'll go over all the solid state material in detail and including semiconductor. Our main subject in this course is to, as I said, to understand the motion of electrons inside semiconductor. Okay, now before we go into the material, we'll present to you some important quantities that we will be using in the when we apply problem sessions on the topics that we will cover. So the electronic charge, and these constant, by the way, will be always given to you in a table during exam or assignments or anything. So nothing for you to memorize. Plus more parameters will be given depending on the question and the constants that involved in the question. Electronic charge is 1.6 times 10 to the minus 19 coulomb. The permittivity of a free space. This parameter will be very important and we'll look at it with respect to free space always, since it's constant in free space, but inside the material, depending on each material. So the permittivity of a silicon will be different from the permittivity of germanium, and so on. So in free space, it will be equal to 8.854 times 10 to the minus 14 per centimeter. And this parameter will be, the permittivity in the material will be relative to this one. For example, we'll say the permittivity of silicon to the free space, permittivity is equal, for example, to 0.6. So you will know how to calculate your permittivity in the material. Boltzmann constant 8.62 times 10 to the minus 5 electron volt per Kelvin. Planck constant, it's 4.14 times 10 to the minus 15 electron volt second. The free electron mass, as well, for every material, we will compare the mass of electron inside the material with respect to this mass, the free mass, which is 9.1 times 10 to the minus 31 kilogram. As well, at room temperature, as you recall, we did use this parameter. We said that it's a 26, between 25 to 26 millivolt. So KT over Q then, and this really came, this value, we use it when we compare if you recall, when we use the diode current with respect to the voltage given at room temperature in application. Here we need it because we will always go to room temperature to be able to calculate the concentration of electrons inside the semiconductor. And of course, 1 electron volt is 1.6 times 10 to the minus 19 joules. Okay, so here is the chemical table for semiconductor, not only for semiconductor material as a chemical table, but we will look at the semiconductor material. When we say elemental, like we have in semiconductor, elemental and compound and alloy material. Our concern will be with, mainly we will describe the elemental, as well we will go through some of the compound material in this course. The elemental is such as carbon, silicon, germanium, and so on. So these semiconductor material that used in most electronic devices, where you will have silicon or germanium being used as for, transistor for diode. What it is, it has, this is from table 4, so it has 4 electrons in its outermost shell, while the compound material such as gallium arsenide or gallium phosphate or gallium nitrate. So what it is, it takes from group 3, added to it group 5 to make a compound which will have as a combination 4 electrons in its outermost shell. So when we are saying elemental or compound, we're talking about material, elemental used for electronic devices, compound used for optoelectronic. What we mean by that, it's very good for measuring, like for light measuring, for sound measuring. So it is an active, we say this is an active device. So it's good, and we will go over each one of them in detail. Okay, in this slide, what I try to show you is just the typical, if we go from hydrogen to silicon. What do we mean by that? If you look at the orbital structure of hydrogen, you will see that hydrogen only has one electron, which is in the table here. You see it occupies n equal to 1 in the 1s orbit, so it's only have one electron, and that's in its outermost shell. While for silicon, as you see, it occupies, if we go down to the silicon, you see it filled up the first orbit, the N1, it filled it with 2 electrons in the S and 2 in the 2s and 6 in the 2p. So what's left in the 3, where n equal to 3, as you see here, it has 2 s is being occupied, 2 electrons, and only 4 in the p instead of 6. So it has 4 electrons in its outermost shell. And these 4 electrons, what they do is try to make a covalent bonding with other silicon material. If we are talking about a pure silicon, meaning a pure semiconductor before any doping, then we say that the crystalline structure, it makes from so many atoms that will each share these 4 electrons in its outermost shell with other atom, so to form a covalent bond and to form the crystalline structure. So we will be looking at what I mean by the silicon atom here, how it is formed. As you see, the orbit, and it has, as we say, the nucleus has 4 protons and 4 neutrons, 14 protons and 14 neutrons. And it has 4 electrons in the valence shell. So these 4 electrons that are able to do the covalent with other material, with other silicon atom. So here is the atom, and this is what I meant by the crystalline structure, and that in solid state physics you will go over so many different material, different solid material, including the semiconductor. The semiconductor has the type, if it's an elemental, we say, such as silicon, we're talking about a diamond cubic lattice, so it has the face cubic center structure, as you see in here, and its lattice constant is 5.431 angstrom. Okay, so here we want to know, if you have a silicon atom, okay, how many atoms do you have per cubic centimeter? So we want to know the density of silicon atoms. We're talking about 10 to the power 22 atoms per cubic centimeter. That would be for the silicon atom. So here it's describing to you the number of atoms completely inside the cell, number of electrons, number of corner atoms, how many you have on each side, and how many you have on the faces. Okay, if we're talking about compound semiconductor, then with the compound semiconductor, we have zinc blende structure. Okay, we said for elemental, we have the diamond structure. For compound, we have the zinc blende structure. And as I told you, that it is important for optoelectronics and for high-speed IC as well. Okay, this is the crystal graphic notation, we use the Miller indices. With the Miller indices is just to, what we mean by Miller indices is like 100, 010, 111, 110, and I will explain to you what do we mean by these indices. It's just to tell you, mostly for silicon material, it will be the 100. So it's along the X direction. So the Y and the Z and the Y direction does not have the atoms across it. So it's all along the X direction. And that's what we mean by the HKL, the crystal plane. So the crystal plane for silicon, then it's along, we said, the 100. So the Miller indices, here we have H is 1, K is 0, and L is 0. So this is what we mean by Miller indices. Okay, if you find I'm going too fast, please, you can interrupt me and say to slow down. I have no problem. Okay, with the crystallographic plane and silicon wafers, we're talking about the silicon wafers. As I said, the silicon wafers will be in this configuration, mostly in the plane configuration, which is the 100. Okay, you might have 110 and the 111. The 111, as you notice, it will have on each corner of the cube will have an atom. So it have on the X, along the Z, and along the Y. So in here, the 111 stands for H equal to 1, K equal to 1, and L equal to 1. In here only it has on two faces, on this face and on this face, so it have along the X and the Y and not along the Z. And in here only has along the X direction. Okay, so as we are describing again, we're saying that the silicon wafer are usually cut along 100 plane with a flat or notch to orient the wafer during the IC fabrication. So all this crystal graphic plane and the wafers is to give you a, an idea about how the semiconductor are fabricated. How do we make the silicon wafers? Now, for you, you're not in this course going to do any, fabrication. Mostly it will be physics. This lecture is just for you to start, but the main lecture will start with describing electrons and so on Thursday. So this is an overview of the semiconductor material. Okay, here as you see, if you have a unit cell of silicon, okay, depending on the cut of this, if we take this cell and we cut it, depending on the wafer or on the plane that we cut it, here is the view, we say, of the 100. Here is the view if you have it in the X and Y, and here if you have it in the X, Y, Z direction as a cut of the crystal structure. Okay, electronic properties of silicon. Silicon, we say, is a semiconductor material. Pure silicon has relatively high electric resistivity at room temperature, That's why you will find in electronic devices such as the diode and the bipolar junction transistor, as well as the field affected transistor, on any IC chips you will use, they use the silicon material, since the silicon material has a high electrical resistivity. So it does not get affected with the temperature if we are at room temperature. Of course, at a higher temperature, things change. Okay, in electronic properties of the silicon, we're talking about two types of mobile charges. What do we mean by that? Recalling from last year when we said that the semiconductor material has two bands and there is a gap between the two bands. Okay, one of the band called the conduction band, the second band is called the valence band. And we know for pure material at room temperature, before any temperature gets raised or anything, we say that the conduction band is empty and the valence band is fully charged with electron. Now, when the electrons get excited due to temperature or due to doping, that will make an electron to go from the valence band into the conduction band, then it will leave a hole behind in its place, you know, a vacancy in the valence band, which we will refer to it as holes, as a positively charged okay. So here what we are saying, we want what you will learn in the next lecture is when we go talking about concentration per cubic centimeter. So usually we want to know how much concentration of electrons are in the conduction band, how much we have in the valence band as holes. And this, of course, you know, like will happen if we change the temperature on a pure silicon. So we're, in this case, if it's only done by temperature changing, we will refer to it as an intrinsic material. If we have an impurity added to the atom, then we'll say that we have an extrinsic material. If it's done by applying an electric field or an irradiation, so then in here we'll be talking when we reach to the electrical properties of the material or the optical properties, and we will be then describing the conductivity and the mobility of electrons. So we will go one by one with the material. So let's look at the bond model of the electrons and holes. Here, as you see, this is a presentation of the crystalline structure of a semiconductor made of silicon. As you see, silicon beside another silicon atom beside another silicon atom, and as you notice that this two electrons here, two electrons, two electrons, two electrons, those are the covalent bond of the sharing electrons between this atom and that atom, between this atom and the neighboring atom from here, or the neighboring atom from above. Okay, so then when we look at these two electrons in here or in there, we're saying that this atom is sharing its 4 electrons with its neighboring atom, another 4 electrons, to form a covalent bond. Now, as temperature, let's say we're still talking about just the pure silicon. If temperature have raised, what will get is this electron get excited and move away. So to the conduction, we call it a conduction electron. That means the silicon electron from the valence band have moved to the conduction level, leaving behind this vacancy. So it created a hole. So in here we say that then we have an electron hole pair. Okay, so in here we said that positive charge then is associated with a half-filled covalent bond, moves when an electron from a neighboring covalent bond fills it. Okay. Of course, this happens, as we said, that the conduction electron, what caused this electron to get out from here, it is by raising the temperature, and that forms an electron hole pair, as I have just mentioned. And we're talking about here a pure intrinsic carrier concentration that we refer to it as Ni. As you notice here that Ni with respect to temperature for every material, it's different. So when we try to, let's say, calculate the concentration of a doped material or of an N being in the conduction band, we will try to depending on the temperature, if it is Ni, then it's constant for every material. Like silicon has different Ni from germanium, from gallium arsenide, from gallium phosphate, and so on. Of course, at a very higher temperature, it's no longer constant, but we're referring to it as taking just the linear and saying that at room temperature it will be fixed and have given one value of intrinsic concentration. So here the silicon then, it's roughly 10 if we look here, so it's 10 to the 10. So we are saying that we're referring to this value of silicon at this point, at 10 to the 10 per cubic centimeter, if we're talking about room temperature. So it's fixed at room temperature, we can take it as 10 to the 10 per cubic centimeter. But if we have different temperature, then we have to calculate the concentration of electron for silicon. What I mean by the concentration of silicon, meaning the N. So we refer to the number of electrons per cubic centimeter as N, P for holes, and we say the intrinsic carrier concentration. So in pure semiconductor, N equal to P equal to Ni. So there is no difference between N and P, because in pure material it's only caused by the temperature that will put an electron in the conduction band, leaving a hole or a vacancy in the valence band. So as the number goes to the of N goes to the conduction band, there is an equal amount of vacancy in the conduction, in the valence band, since this is a, what we say, a pure material, has no other material in it. So the same number, still the same. Okay, so this is the last slide for today's lecture. And after this, I can stop the recording, but we can continue with any questions that you have. So in summary then, what we have went through today, we said that we looked at the crystalline structure of silicon. We said that silicon has 4 valence electrons per atom, and it is made, since it's an elemental material, it's made of diamond lattice, and it joins 4 electrons with its neighbors. It has an atomic density of 5 times 10 to the 22 atoms per cubic centimeter. The intrinsic concentration is 10 to the 10 per cubic centimeter. We use the Miller indices to give us the direction within the crystalline lattice. And in pure silicon crystal, we said that the conduction electron and the holes are formed in pairs. So as you see, electron-hole pair, because meaning that as we the amount of electrons in the conduction band equal to the amount of holes in the valence band. We consider the holes as being the positively charged, and both holes and electrons can conduct current, we say. Although it's a vacancy, but we say we will have a conduct current due to electrons as well